Hi everybody! Today I wanted to make a video showing off some of the in-person demonstrations that I do to highlight optical mineralogy. Some of these demonstrations involve using a specially built polariscope in order to project interference figures. I've picked out some of the best ones to take a look at today. Here we have a flashlight, a polariscope specifically designed to project interference figures, and 3 of my favorite samples. This setup is similar to a conoscope. However, for today I'm going to call the polariscope that's specifically designed to project interference figures the polarojector. Let's take a closer look at a side view of the polarojector to figure out what it actually is. This consists of a flashlight, which is our illumination source, and this flashlight is a normal LED flashlight that you might have in your house. Because it is an LED flashlight, it's not really the full spectrum of light, but it'll be good enough for our purposes today. This flashlight also has a converging lens, which allows us to direct the light going through our sample. The light then interacts with a material to diffuse the light, in this case just a piece of tracing paper. The light then passes through a lower polarizer, which causes it to become plane polarized. The light will then travel through and interact with whatever sample we have in our sample area, and will then finally go through our upper polarizer. This polarizer is perpendicular to our lower polarizer. The output from this will be an interference figure for our sample. Let's take a look at the different samples that we're going to be using today. First up is a piece of synthetic corundum. This is used in a variety of industrial and scientific applications. You may know this better by the colored gemstone variety names of sapphire or ruby. Those are both the mineral corundum, however have different impurities generating the different colors we see in sapphire and ruby. There's an entire video detailing the nitty-gritty details of corundum if you want to check out Snellius Minerals LLC corundum kit. If you have checked out those videos, the following figures I'm adding on here are basically a summary of what's going on with our mineral corundum. But for the really big overview today of what we're doing, it's just sufficient to say our minerals are defined by their chemistry and structure. This in turn determines the symmetry of our minerals as well as their optical properties, and how these properties vary with direction through any single crystal of our mineral. Next up in our samples for today is our natural quartz slice. There's another educational video detailing quartz slices, and that is Snellius Minerals LLC quartz slice. And once again, we have some summary figures here that detail the relationships between our chemistry, structure, symmetry, and optics of our quartz. The last sample we'll be taking a look at today is a piece of muscovite mica. Muscovite mica is investigated more in depth in the educational video Snellius Minerals LLC Oriented Muscovite Sheet. And again, there are some summary figures taken from that video to illustrate the relationships between chemistry, structure, symmetry, and optics. Now for the fun part. Let's check out what each of our samples do when we put them in our polarojector. Here we have our flashlight shining through the polarojector, and you'll notice not really much of anything is happening. A bit of light is coming through because the linear polarizers are not perfect. Our first sample will be our piece of synthetic corundum. We're now adding that into the polarojector, and if you look up on the ceiling, you'll see a uniaxial optic axis interference figure. So I want you to remember what that pattern looks like, because now we'll remove our corundum and we're going to switch over to our next sample, which is our natural quartz slice. Quartz, like corundum, is actually uniaxial. However, it has a special power that corundum does not, called optical activity, and so it actually ends up generating an interference figure with this distinctive circle at the center. If you can generate this interference figure for a material, that material is almost certainly quartz. There's only a couple other options it could be, and they're all very rare. Lastly, we'll take a look at our muscovite mica. Our muscovite mica is going to be biaxial, and the interference figure we're going to see here is not along the optic axis. It's something called the BXA, or acute bisectrix interference figure. With our earlier interference figures for quartz and corundum, if I were to rotate the specimen, nothing would have happened, but for our biaxial muscovite looking at the BXA, as the specimen rotates, you'll notice all sorts of fun things going on. The really big picture of what's going on here is that we can use light interacting with the structures of our minerals in order to understand something about our minerals. The interference figures that we see result from the symmetry of our crystal structures. We can use the optical properties of our minerals to identify different mineral species, understand which direction we're looking through a particular crystal of a mineral, and then possibly use this knowledge to build high-tech components of our modern lives. We recently detailed how interference figures were important for the development of the optical ring sight by Polaroid during World War II, and I'd suggest picking up a copy of the book Rings of Fire to learn more. There's a whole bunch of minerals for learning about optical mineralogy available at the eBay store Snellius Minerals. I don't have any of the large-scale polarejectors for sale on the eBay store. However, if you want to contact me to possibly have a custom order, feel free to reach out at snelliusminerals@gmail.com. Here are the references that I used in creation of today's video. Thank you again for watching, and have a great day.